Log on, tune in, find out. Another good idea from Cambridge.
First, it will talk on localization in quiver moduli spaces and the refined grammar-Twitter correspondence.
Okay, thank you, and thank you for giving me the possibility to speak here. So, as said, the topic of my talk is localization in quiver moduli spaces. And we find GW or Chromophyton Kronecker correspondence. So on the one hand, we consider the Euler characteristic of moduli spaces of stable representations of certain bipartite quivers. I will explain this later. And on the other hand, we consider GW invariants of weighted projective planes. So they are somehow linked between the they are linked considering the tropical vertex, which is a group of formal automorphisms, but I don't want to say much about this link. I will somehow give this correspondence, and later I will explain more about calculating these Euler characteristics by localization or by considering a torus action on these moduli spaces. So let's start, and we fix the field to be C, and then we have a quiver Q, which is given by the vertices Q0 and arrows Q1, and this quiver should not have oriented cycles, so without oriented cycles. Then we fix a dimension vector of this quiver and consider the affine K-space of representations, which is just the direct sum of these sum spaces. Okay. So now we want to define a stability condition on this representation. So we fix a linear form theta, which is in Hom ZQ0 Z. Then we define the linear form dim to be the sum over all vertices, and here we have Q star. Yeah. Okay. So where this is just the Kronecker delta, so this Q star, Q prime, this is just defined to be the Kronecker delta Q, Q prime. Okay. So, and then we define a slope function. By saying that mu of d is just theta d divided by dim d. So, and then we have the usual notion of stability. So we just say that a representation is stable if all sub-representations have strictly smaller slope. Okay. Then we have a moduli space for these stable representations, which we denote by MSDQ. Okay, this is RDQ, and we mod out the action of GD. GD is the direct product of this GL dq. Okay. Okay, this is the moduli space of stable representations, and this is a smooth variety. And it is also projective if semi-stable equals stability. So if semi-stable is equal to stable. So okay. Okay, and these are just results of King. Okay, so now we want to consider another stability condition. So we don't just consider these representations. We want to define some frame moduli spaces and to get some conditions or some link between the generating functions of these Euler characteristics and the generating functions on this side. So I will restrict to the following quiver and the following. So we consider the quiver Q. This is denoted by K, L1, L2. And this quiver has vertices I1 to IL1. Yeah, and J1 to JL2, and we have arrows going from J to I for all J's and I's. So so now we can consider some ordered partitions of length L1 and length L2. So and then we can understand this partition as a dimension vector of this quiver. So let P1, P2 be an ordered partition or a tuple of ordered partitions. Where we allow entries to be 0. Okay, and this defines the dimension vector D P1, P2 in NKL1, L2 naught. Okay. Okay, now we choose a stability condition on this, we choose a stability condition as follows. So let theta I be equal to 0. That's the other way around. Yeah, 0. Theta IL and theta j k is equal to 1. Okay. Then we consider the following tuples. CK, WL, F, LK, WL, so this small one. With dim So we fix this partition here. So, and we have dim vk, this is equal to p1k, and dim wl, this is equal to p2l. And then these are just linear maps, so this is, we have on the one hand we have the representation of this quiver, but then we have the additional data, which are these WL, and these WLs are just vectors in our vector spaces WL. So these are vector spaces of dimension P1k and P2l. So, and this tuple is called stable. If it is semi-stable with respect to this stability condition here, defined by this linear form, and then so this is equivalent to the following condition. So we have sum over all k, sum over all l, fl k ul. So here we have the sum over all L dim UL. So semi-stable with respect to this stability condition we have chosen. And the additional condition is such that we have strict inequality if these WLs are elements of this ULs. Okay. Okay, now we consider such tuples up to base change, and then we have the following. So we consider tuples up to base change. So that just means that we say such tuples fkl, wl, this is equivalent to fkl prime, wl prime, if there exists gk in gl, vk, and hl in gl, wl. This is equal to gkf kl prime hl to the minus 1. And we have also that wl prime is equal to hl wl for all k and l. Okay, so if we consider this setup, we get a moduli space for this tuple. So we consider these tuples up to this equivalence, and then we get the theorem by Engel and Kronecker. So this is, there exists a moduli space which parameterize these tuples, so up to isomorphism.
Why isn't this just a moduli space of representations of a quiver with one extra vertex?
Yeah, okay. So in you can define this more general, in a more general setup. Okay, yeah, probably you're right. But you don't consider this G action on the additional vertex.
It says what dimension vector 1 there.
Yeah. Okay. So if it's okay in this setup.
And this is
Okay. Yeah.
It's just a technical.
Yeah.
You're making it look complicated. It's not complicated.
Yeah. That's true. Yeah. Okay. Yeah.
That's all.
Yeah.
Not new.
Okay, yeah. Okay, we have a moduli space MB P1, P2, parametrizing such equivalence classes. Of stable tuples. And this is a smooth variety again. Okay. Yeah, okay. And so if the dimension vector is theta coprime, so semi-stable is equal to stable, concerning the representations there, then this is just a P, what is it? A P, this, okay, so that writes down. If D is theta coprime, this is a P to the P2 minus 1 fibration over the moduli space we have for the representations. KL1, KL2. So, thus, if we have such a theta coprime dimension vector, we can easily calculate the Euler characteristic of this guy here if you know the one from this guy. Okay, so now we consider the generating functions of the Euler characteristics of this. So let FA B to the B, so that's just an index here, the generating function, so that's the following. So we sum up over all K and all tuples P1 and P2, so such that P1 is equal to Ka, P2 is equal to Kb. And then we consider the Euler characteristic in singular cohomology of this guy. So and this is just S1 to the P1 1 to SL1 to the P1 L1. Okay. So now on the other side we can consider Gromov-Witten invariants. I don't want to go into detail there, but so roughly speaking they just count rational curves on weighted projective planes. So consider GV invariants NAB P1 P2 and okay, so roughly speaking counting on projective line on weighted projective lines PAB1. So and then these partitions say which with the multiplicities of these curves. Oh, okay. So no, sorry. So this partition says or gives some extra conditions for this rational curve. So they have to intersect these divisors with multiplicities given by these partitions. So, but I don't want to go into detail here. So, with some extra conditions. Given by P1 and P2.
But is there a way to say, if I started out with the weighted projective space, plane, which is the sort of thing I might actually look at, how this other thing would have come into the picture? Let's say I was just sitting there with the weighted projective plane. How would I ever start thinking about this quiver and why would I expect something like this to be true?
So sorry.
Is there some kind of overarching geometric reason why these two things should be related?
No, there is you get these connections between these generating functions just considering the tropical vertex, and you somehow in the end it's on both sides it's the same. So the geometric reason is quite unknown. So I don't. So
how's the quiver associated to the weighted projective space? Is there some exceptional collection on the weighted projective space or something?
Yeah, right.
This is the endomorphisms of.
yeah, so you have this partitions of length L1 and L2, and this gives you the quiver. So you fix the length of the partitions here.
Uh-huh.
Okay. So on the one, so the quiver looks like
I think
so.
it's entirely mysterious.
Oh,
This-
really?
This is the quiver here. So J1 to JL2,
No.
Right.
I1 to IL1.
Talk had that flavour.
Okay, and this is the quiver, and so every partition of length L1 and or every tuple of length L1 and L2 gives you a dimension vector here. Okay. So that's the connections, the connection between these two
It's
guys.
not the quiver, because privately there's another vertex.
Yeah, and you have an additional vertex here. Okay. But the quiver KL1, L2 is this one.
But that's, you're free to, yeah, but that's not the quiver that, in the story, you've hidden this extra vertex.
Yeah, you have this, but this is this quiver here.
Yes,
Yeah.
sure.
Yeah. And then you get this vertex here of dimension 1. Yeah. Okay.
Say again what A and B are?
Oh, sorry. A is just the length of this. So you fix some A and some B and the partition, the value of the partitions. If you sum up the partitions.
Okay, can you read aloud what the third weight of your weighted projective plane is? It's A, B, and?
One.
Sorry.
So here you fix A and B. And on the quiver side, it's just the sum of the dimension vectors on each side.
You KA and KB.
Yeah, but you sum up here about over all K. So you fix A and B, and then you sum up over all K, so that P1 is the sum of the entries is KA and KB here. Okay.
So the number of vertices in the quiver doesn't interact with A and B.
No, but you fix some length in. So yeah, you fix somehow L1 and L2, and then you fix A and B. Okay. So you consider all partitions of length L1, so that the entries, if you sum up the entries, it's A or KA and KB. Okay.
Right, so this doesn't, yeah. This is to do with the intersection properties.
But
You didn't tell us what exactly these Kronecker invariants were, but that's somehow where the L,
yeah,
these extra vertices are hidden.
so I just give an example later.
Yeah, that's good.
Okay, so what we get is so So now we have to apply several results. So applying results of Großpanda, Ripande and Siebert on the GW side, and the results we had, and some other results. Most of the results are due to Kronecker, I think. We get that so we fix L1, L2, and then we consider all partitions of length L1 such that if we sum up about overall entries, this is Ka, Kb respectively. So then we have K times the Gromov-Witten invariant here. So S to the P1, T to the P2, X to the A, Y to the B, to the K. And this is equal to F AB to the 1 divided by B.
I don't just like go at this discussion. And I know on the one side, I think there's some scattering diagram is where the Gromov-Witten invariants are on one side. Is there some similar thing in the picture of these quivers? Is there a scattering diagram? Is that why the
if you not really, but if you consider this localization method, then you get some new quivers or some sub-quivers of this KL1, KL2 in this case, so which are a bit look like these scattering diagrams, I guess.
Some mutations or something, or something that has to do with the in the scattering diagram. There's these sort of transition.
Yeah. I don't.
I mean, I'm wondering how you use this paper, Großpanda, Ripande. To me, it's a statement about output in the scattering diagram.
Yeah, it's more the paper due to Gross and Panda Ripande, and then the other ones.
I know that one. I don't know.
Yeah. So yeah, you really consider this generating function, and this then you consider this formal automorphisms and the tropical vertex, and that's the
ring
link.
itself. I get it.
Yeah.
I mean, Großpanda Ripande proves that the numbers you get out of these crazy scattering diagrams are the numbers they are the Gromov-Witten.
And they are just something in this vertex ring.
Right.
I got you.
Okay, and on the quiver side now, we know how to get, or these generating functions are given by functional equations. So we have.
So can you say again how many symbols are there in the right-hand side? What this is? Can you read this? F.
A b to the b. This is just the generating function here.
What's the upper B?
This one. That's just some index so that.
Relationship between the two B's.
Yeah. Okay. So you can get rid of this.
The same B, but he's looking at the backwards frame.
Yeah, it's,
He's putting his framing at the back.
Yeah.
So
yeah, just forget about the b. So
What's 1
it's
over
not.
B?
It's sorry.
It's 1 over B,
Yeah, that's 1 over b. Yeah.
which is the same B.
No, it's not the b here is for back frame. So, but you can forget about this. So just some notation.
Whereas 1 over B really is the same B as the B and AB.
Yeah, this is the same b. Yeah. Okay. So yeah. Okay. Okay, so let's denote this by FAB. So we know that these guys are given by functional equations, and then we get that this FAB is given as follows. So we have P1 to Ka and P2 is equal to Kb. Then we have some formal power series denoted by R P1 P2 times K to the K times chi P1 P2. So this is now the Euler characteristic of dP1 P2 of KL1 L2. So here we have the original moduli space, not the backframed one. So sorry about the confusion. Okay, so these guys are given, and now these RP1, P2 satisfy the following. So that's just prime is equal to Ka, P2 prime is equal to Kb, Rp1 prime, comma Rp2, P2 prime, and we have minus the Euler form d P1 P2, comma d P1 prime P2 prime times the Euler characteristic of this guy. Okay, so that looks horrible somehow, but if you know something about the Euler characteristic here, so you know something about, this guy here, and if you know this guy here, you can compute this Gromov-Witten invariance here. So that's some nice stuff. So if you really, and there are many cases where you can compute this Euler characteristics here via localization. So and sometimes they vanish, so you get that this simplifies dramatically.
What's the little f of AB?
So,
Yeah, small f is the same as capital F.
no, this FAB is this guy here. This x of. Okay, so sorry.
What is little FAB?
That's this one here. So.
Oh, sorry. Yeah.
Okay, so and now if A and B are co-prime, so we can and P1 is equal to A and P2 is equal to B. We have the Euler characteristic of P1 and P2 is equal to NAB P1 P2. Okay, so now so that just follows if you consider this functional equations a bit more detailed. So then you see that really if you have co-prime AB, then you can just by comparing coefficients that you see that these guys are equal. So now we want to compute or we want to consider some examples and calculate the Euler characteristic on this side, and this gives you the Gromov-Witten invariance on the other side. So what we do is we consider torus action on the moduli spaces so that P be equal to C star to the Q1, so for quiver Q, and this acts on RDQ via scaling. So we just consider T alpha times X alpha. This is equal to T alpha X alpha for some representation X. Okay. And this induces a T action on the moduli space. Okay. So in the representations, or the Chur's fixed points of these moduli spaces, they can be described by representations of the universal cover. So we consider another quiver. This is Q tilde. This is just Q naught times Q1 in brackets, where this is just the non-commutative group generated by arrows and its formal inverse. And we have the following. Okay, so Q tilde with and we have arrows alpha I W going from IW to J W alpha, where alpha is an arrow from I to J and W is just a word in this group, an element. So we just want to consider connected components. So if we have, so for example, if Q is equal to the 3 Kronecker quiver, then the connected components of this quiver just look like the following letters. So we have some quiver looking like this. And each arrow here corresponds to an arrow of this original quiver. So for instance, this is alpha, corresponds to alpha 1, alpha 2, alpha 3, and so on. Okay, so then we have that these guys, so I will say what this is, they embed into the Chur's fixed point set of, with respect to this action there. So where here we consider equivalence classes of dimension vectors of this guy here. And equivalent class, so we have that 2 dimension vectors are equivalent if they can be translated into each other. So if we translate, so we have some action on the vertices given by just multiplying with arrows. So IW goes to IW alpha. So we just consider this dimension vectors up to this equivalence.
Not 3 modules. This is not one dimension vector 1. D tilde isn't 1 everywhere, is it? Or not?
It is not, no. Overall. Of dimension vectors. such that if we sum up over all elements of Q1, we have di w tilde is equal to the original di for all vertices. So and if we iterate this process, so if we, after one step, this torus fixed points are representations of the universal abelian cover. So, but the universal abelian cover has somehow cycles in it, and because they are representations of some other quiver, we can localize again, or we can again consider such a torus action. But after finitely many times, we get the following. There exists an m in n such that m is the q t n prime, so that's just relocalized n times, where we have to choose the torus here appropriately. This is again, so you get some isomorphism here. So really, after the remaining fixed points after finitely many steps are just representations of the universal cover. Okay. So, and what we get with this is some corollary, which says that the Euler characteristic of this moduli space is just given as the sum of the Euler characteristics of the universal cover, where we just have to sum up overall the tilde again compatible and equivalent, or overall equivalence classes compatible with the original dimension vector D here. Okay. Okay, so now perhaps some examples. So we consider the quiver Q equal to K23. So this is just this guy here. And now what we need to know, or to know when what dimension vectors we have to consider, we have somehow find subquivers of the universal cover which allow stable representations. So the universal cover is just given by this one. So, or the connected components, and here again. So we have to find somehow dimension vectors of this guy here, which allow stable representations. And if we sum up the dimension vectors of the sources and the sinks, we have to get 2 on the one, 2 and 3 respectively. Okay. So this. Oh, sorry. I should have said that I consider the dimension vector 2, 3 as well. Okay. So A, B should be 3, 2. So sorry. So we have 2, 3. We consider the quiver 2, 3. That says the length of the partitions is 2 and 3 on the one hand side, and on the other hand we have the dimension vector AB given by 3, 2, which just means that we consider such dimension vectors which sum up to 2 and 3 here. Okay. So. Sorry?
The other way around.
This A corresponds to the I, and this is the sinks di. Okay, so yeah, but it doesn't matter, so you can switch it anyway. So
Your theorem is for just these special type of quivers or more general like this?
this one,
Yeah.
that's general, so without oriented cycles.
Without-
Okay, so we have to consider this guy here, so that's the dimension vector, and this guy. So this are real roots of these quivers. This is the dimension vector here. So the Euler characteristic is just 1. But now we have to somehow look how we can embed this guys into this one here. Okay? So in this embedding somehow corresponds to some coloring of the arrows here. So each vertex here has to correspond to some error of the original quiver. So this one can correspond to this one or to this one. And yeah, these guys have to correspond to one of these 3 arrows, vertices here. Okay, so what do we get? So we fix the partition 1, 1, 1, 1, 1, and then we just have this quiver here. So how many choices do we have to color this arrow or this vertex here? This has to correspond to this one or to this one. So we have 2 choices here, and then we have 3 choices here and 2 choices here. So we have 12 choices. And then we have to mod out the S2 actions because we have some symmetry in this quiver. So we get that this is 6. Okay. And okay, so we can make another example. So this is just 1 because we have no choices. This one has to correspond to this guy here, so that's the dimension vector of the original quiver here. So we would consider this dimension vector here. Okay, so in this it's just the same.
Where the 2 goes doesn't make a difference.
Sorry?
Where the 2 goes doesn't make a difference. But because it's ordered.
Yeah, so we consider ordered partitions, so that
So 2 plus 0 is not the same as 0 plus 2.
yeah.
That's an unfortunate notational choice.
Yeah, we have ordered partitions, so yeah. Okay, yeah.
Okay, sorry.
Okay. Okay, so that's one more thing. So if we consider, so I'd like to give an example where the Euler characteristic vanishes. So and then we can compute the central slope of this f. So we can compute this f11. It's not there anymore. So and this is the case where the dimension on the left-hand side, or the sum of the dimensions on the left-hand side and on the right-hand side is the same. So in general, if we consider a bipartite quiver, ij q1,
You're not going to tell us what these 2 Gromov-Witten invariants actually count.
yeah, okay, so I can tell. Yeah, sorry, I forgot. Yeah. I just make so. Yeah, you have this. Okay, so we want to know what this is. So you fix 2 partitions of length. So P1 is equal to P1 L. So where this L goes from L to L1, from L is equal to L goes from 1 to L1, and P2 is equal to this guy here, P2L. So and then you look, okay, and then we fix A and B. That's this one here, and we consider PAB1. And there you have this toric divisors D1, D2. Okay, so we have T1, D1, D2, and D out. These toric divisors. So and then you choose.
You mean out?
Yeah, it's just notation stuff.
Sorry.
So you have 3 divisors.
Yes. 1, 2, and 3.
Yeah, but that's the notation of Gross Siebert and Pandari-Pandit, so I just pick that. Okay. So, okay. So and then you consider such rational. So roughly speaking, these NAB P1, P2. Where do I have this? I did just notation. Count rational curves on PAB1, passing through L1 points of D1, L2 points of D1. So we remove the torus fixed point as well. D2. Naught. And which are tangent with multiplicities given by this partition P1L and P2K, and which are tangent to this D out of order K. In case I didn't fix the K, but yeah, so that's the K which appears in the formal in the generating function, you know. Okay.
These points are fixed.
It doesn't depend on the points. You can choose any L1 points or distinct
They
points.
are fixed.
Yeah, you can fix it. Yeah.
There's the point of tangency. The order K tangency is not fixed. The others are.
Yeah.
Picture, I mean, yeah, what we've shown isn't here, but I mean, draw a picture which would look very similar to what we used to.
Yeah. Okay, so so we had this. So we have this bipartite quiver here. So and we want to consider a subquiver of Q tilde allowing stable representations and the dimension vector. Such that the moduli space is not empty. Then let d I be equal to k times dj. So now we fix such a subquiver Q tilde, and this Q tilde and this Q tilde has a subquiver of the following form. Okay, so and if we fix a stable representation of such a quiver Q tilde, and this is a subquiver, this has a sub-representation of dimension vector 1, 1 to the 1 here. So D tilde of this type. So what we know is that this n here has to be greater than k times 1. So then, if we just consider the stability condition I mentioned in the beginning, so then we get that n has to be greater than k times 1. So we have just this sub-representation, and because the sub-representation has to be of smaller slope, we get this condition here. Okay. And we can do the same for, if we consider a subquiver, we fix some sink and we consider a subquiver of this type here. Then we get some similar condition. So if k is equal to 1, we get here that each source has to have 2 neighbors. That is this condition. So if k is equal to 1, the number of neighbors has to be 2. And we can do the same for sinks. So we get every vertex of Q tilde or of, yeah, okay, so we take this support, so we take just the subquiver where this D tilde does not vanish, so that's the dimension vector we fixed there. But that's not possible because the universal cover has no cycles in it, so we have that the dimension vector we started with is just 1, 1. So okay, so in our case we get that the Euler characteristic of this guy vanishes for all. So if P1 is equal to P2, is greater or equal to 2. And this simplifies the functional equations dramatically. So we get that F11 is equal to the following. So we get this functional equations here. So now the last thing I'd like to mention is, so oops. So if we specialize this sk in TL to one variable t, then we get the following formula. I have to make some more. Sk and TL to one variable t, we get that f11t is equal to k greater equal 0, L1 times L2 minus L1 minus L2 minus times k plus 1 times L1 minus 1 times L2 minus 2 times k over k times g squared x times y to the k to the L1 times L2. So this confirms some conjecture of gross panda repanda. And yeah, so okay, so thank you very much.
Questions?
So I mean, if I give you a specific quiver, does your theorem always give an effective algorithm to compute your Euler characteristic?
Yeah, the problem is to compute, so to compute the dimension vectors where you have stable. So you basically do the following. So you consider dimension vectors which allow stable representations, but you get rid of the coloring of the arrows, and afterwards you consider, or you look at this quiver and count the number of colorings you have in order, in how many ways you can embed this in the universal cover. So, but the problem is, the Euler characteristic of this guy is not always simple to calculate. So, but in many cases, this gives an algorithm. So you can somehow, if you know some localization, such a quiver and a dimension vector, you can glue other quivers to it and get new quivers, which also give some, which also gives some stable representations of the universal cover. Okay. So, for instance, if you have something like this, you can glue always something like this to it, and you get a new subquiver of the universal cover, which allows stable representations. But for small dimension vectors, it's mostly that you just have Euler characteristic 1 everywhere. So, like in this case here. Okay.
Any more questions?
It seems that in good cases you have that this grammar with the invariant, just the same as the other characteristic of something.
Yeah.
In particular, it's an integer. Do you know if that was known obvious for example?
Yeah, so in the covariant case, you get that it's an integer. Yeah.
That was known already. But for the grammar.
I think some parts were known, but not for all dimension vectors, I guess. So I'm not quite sure.
Any more questions? Can I thank the speaker again?